So this brings me back to my initial example where I'm trying to find the definite integral from 2 to 6 for the ln x function with respect to x. I've chosen to do a Riemann sum of 1, 2, 3, 4 rectangles, and I'm going to choose the left Riemann sum. So my 4 equal increments are going to be from 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Since I'm choosing the left Riemann sum, each of my sample points is going to be the leftmost x value for that increment. So my rectangles look something like this. For my left Riemann sum, I'm going to add the area of each of these rectangles. So in order to do that, I have my area of a rectangle formula memorized, base times height. Hopefully you know this too. So in this first case, my first increment has a base of 1 multiplied by the height, which is ln of 2, plus the base of my second interval, which is also 1 multiplied by the height, which is ln 3, plus my delta x here, which is also 1 multiplied by ln of 4, because I've chosen to do the left Riemann sum, and lastly my last delta x of 1 multiplied by ln of 5. If I wanted to, I guess, save time, since I know that each of my increments has an equal width, I could just do the delta x multiplied by f of my c1 plus f of my c2 plus f of my c3 and f of my c4. I have 4 intervals, so I stop at c4. And this actually gives me an answer of 4.78749, etc. as my left Riemann sum. So if I wanted to say whether this was an under approximation or an over approximation of the exact definite integral, I could say that this is an under approximation. Because each of my Riemann sum rectangles is underneath the actual function. Since my function is always increasing, my Riemann sum is actually the lower Riemann sum. So that's a cool thing to think about. And I think that's about it for this problem.